Greetings. We're going to look at 0 divided by 0 here, and I'd like to define this top 0 as the sum from 1 to infinity of -1. So we're indexing this to I, so each number in our index will be the exponent, and then we're going to make this pi sub I. So we're going to have lots of pi that we're going to add up together. Do you like pie? It's delicious. Okay, and then for the denominator, I also want to define 0, but I want to define it just slightly different. So I'm also going to have this be an infinite sum from 1 to infinity, but this time this is just going to be -1. And we're going to disappoint everybody by leaving the pi out. So this fraction is equal to this fraction. Is that true? Well, let's look at some of the first terms. The first term here, this is going to give me -1 times pi, which is -pi. The first term down here is going to be -1. To that, we are going to add the second term. So this would be -1 to the second power, which is +1, and this would be a second pi. So 1 times pi is pi. And then looking at the second term, we get a +1 here. And with this partial expansion of the summation, we see that -pi plus a pi is in fact 0, and -1 plus 1 is 0. So this is just taking this out to infinity, as long as you want to go. So let's add another few more terms into here. Now that we've written this expansion out, because this is just addition and it's real numbers, we can add parentheses in here. That's the associative property. So I'm going to group this pi right here together. So these pi's, we get pi minus pi, that's 0. Everything's 0, that's the way we defined it. We're going to come over here, we're going to group those pi's, and then so on. And then likewise down here, we're going to group these ones here. So 1 minus 1, that's still 0. Everything's 0. We love 0. And then we group this. Well, this is 0 plus -pi here. Delicious. And then this is going to be 0 plus -1. According to the additive identity, 0 plus any real number is just that real number. And likewise down here, so we see that we have -pi divided by -pi is just equal to pi. So we have demonstrated that 0 divided by 0 is pi. All right. So over on his channel, Consistent Determiner has been trying to break the internet by talking about some broken math. He's put up a couple of math for fun videos where he does things like this, where he demonstrated that 0 divided by 0 is 1. And his demonstration is similar to what I've presented here, and it works. And you may have seen a meme around the internet where someone proves that 0 divided by 0 is 2. In this case, I've shown that 0 divided by 0 is pi. How can all these things be equal to different things? So that's an inconsistency. We don't like that in mathematics. This type of thing is not unknown to mathematicians. Is math really broken? When things like this happen, we really have to ask ourselves, what is really going on? What's the underlying thought? What's the underlying philosophy? And importantly, what are the axioms and definitions that we are using? In a classical algebra, we have any real number divided by 0 other than 0 is going to be undefined. So if we let n be a real number, and also n is not 0, then we would say that n divided by 0 is undefined. So that's a classical algebra perspective. You may see other places, other people talking about places where you can divide by zero. You have to step into another algebra for those situations. But right now we're going to look at classical algebra. This is the type of thing that you learned in high school. So we have this as undefined. But I've distinctly said that this real number is any real number but 0. So what happens when we have 0 divided by 0? Well, in that case, we like to call this case to be indeterminate. Since this is indeterminate, it essentially means that you can make the argument that it's going to be any value that you want it to be. As I've done here, I've said it's pi. As it's been said other places, you can see that it's 2 or 1, and really you could make an argument for any real number that you'd like if you can just come up with the argument. Things like this do not work well for consistency, so it's essentially, being that it's indeterminate, we don't use this because we cannot have the consistency that we want in having a logical flow. We want to be able to have something we can assign a truth value to, something else that we can assign a truth value to, and then come to true conclusions so that we have a logical, true conclusion. So this gets into a little bit of elementary logic, which are very foundational ideas in mathematics. I also want to bring in something else that's really interesting, which plays into what I've done here and potential variations that you see of this. There is a couple of theorems called the Riemann rearrangement theorem. And that talks about having these types of sequences where you have positive and negative real numbers. If you look at all the negatives here, they diverge. So we would have negative pi, negative pi, negative pi. Right there we have negative 3 pi right there, but this goes on to infinity. So this really diverges out to negative infinity. And then if we look at the pi's individually here that are positive, we add up all the pi's and this diverges to positive infinity. We have the same type of argument down here as we look at the negative ones versus the positive ones here. We get separately diverging sequences here. And when you look at the Riemann rearrangement theorems, we see that it's the expectation that when you have this, you can essentially rearrange it so that it converges to whatever number you want to argue for, which is how these arguments work. So it's a known phenomenon. I'm going to go ahead and suggest that you check out, if you're interested in this, Terence Tao's book, An Introduction to Measure Theory. And if you want a little bit of a shorter read on this topic, I'm going to direct you to Stewart Galanor's article in Mathematics Teacher, which is a journal. The title of his paper is, I believe it's called Riemann's rearrangement theorem, and the point is that the rearrangements are not unique. I hope those of you that enjoy driving people crazy with these kind of arguments has enjoyed this, and also those that want to know why things like this happen. Hopefully I've given you some ideas about what we're talking about here with the logic and defining things and having things undefined, and how these are important to recognize. You want to really get into the axioms and the philosophies and look at the foundations of the mathematics that you're working with. As you change the axioms, you change the system that you work in. So you could start to investigate some of those foundations and philosophies, types of books, look at different mathematical branches that deal with analysis or point set topology. Hopefully you find some mathematics in your part of the world to enjoy. Cheerful calculations.